Okay, calculus. We are into our section of applications of derivatives. You notice that in the last unit we did 4.4, and so that's taken care of. We're skipping 4.2 and a couple other things. Not that big of a deal, but I think there are some challenging problems in this section. There's no question, but I think you'll do well because you're super smart. So Chapter 4, where applications of derivatives. What do derivatives tell us about things? And there might be a time here, where we will for sure. I've got to kind of organize the unit, but we're going to actually how they use derivatives in the real world. Everything right now is very abstract. Math, we look at these graphs and these equations and what do they mean? They do come up in the real world. So let's start by defining what a critical number is, and we can see what it tells us about a graph. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. So if the derivative is equal to 0 or the derivative does not exist, then it's a critical number. In this situation, you can tell that we have a critical number right here. The derivative does not exist because derivative does not exist at an endpoint. The derivative is equal to 0 here, so it's a critical number. Derivative does not exist here because you can't take the derivative at a corner. Derivative is equal to 0 here, so it's a critical number. Derivative is equal to 0 here, critical number, and again an endpoint, so a critical number. Now we're going to talk about maximums and minimums. Absolute maximum or global maximum is the largest value of a function. And really on a given interval. Absolute minimum would be smallest. So as we start, example 1 says, looking at the graph provided, identify the absolute maximum and minimum values. And so we want to look for the largest and the smallest values. So we don't have any y values here, but we can tell where they occur. So C1, this is where you had an absolute minimum. And then it looks like the largest value is right here. Absolute max. So C1 and C4 produce our absolute minimums and our absolute maximums. We don't actually know what the absolute minimum or maximum value is because we don't have y values, but we know where they occur. A local maximum or a relative maximum is largest value in an immediate interval. And this would be smallest. So the idea is if you kind of box, this is a very rough description, but if you kind of draw a box around a general area, okay, you can see that at C2, this is the largest value in that immediate interval. So if you head to the right or if you head to the left, you can see that at C2 we have our largest value. So at C2 we do have what we call a local max. And in this situation here at C3, that's the smallest value in the immediate region. So if you could draw a box like that and say, well, it's the smallest within that immediate interval, then it's going to be a local min. Now back up here, again, if you box this area, that again is a local max. And then here would be a local min. So you can be an absolute min or max and also be a local min or max. Okay, so those work together. Vermonts theorem. Vermont was a famous mathematician. We talk more about him later, but he said is if f has a local max or min at C, and if f prime of C exists, so let's kind of think about this. So we'll draw a graph that has a local max and a local min. Okay, in both these situations, I have a local max and local min. So we got min and max. Okay. So if f has a local max or local min at a value C, and if the derivative exists, that means that you can find the derivative at that spot, then f prime of C is equal to 0. F prime of C is equal to 0. The derivative will be 0 at that spot. Now, it is possible that there's times where there's a local max or min, but the derivative is not 0. So I'll show you one. Here's a local min right here. And the derivative is not 0, because the derivative does not exist because it's a corner. So when we find the derivative equal to 0, we find these local maxes and local mins, and it ends up being really helpful. So critical points, as we talked about, you have that type of spot. So you have this C value right here where you have a critical point, C value right there where you have a critical point, because the derivative is equal to 0 at that spot. And then you have another spot where we have critical values. I'll skip the undefined, but like a corner. So, the derivatives do not exist at corners. Because they do not exist at corners, that's a critical point. Okay. And then another spot that we need to consider for a critical point is again where the derivative does not exist. Derivative does not exist where you have a vertical tangent. If you have a vertical tangent, then that's a critical point as well. So I want to talk about the undefined scenario. So if we consider, say, 1 over x minus 3, y is equal to, if you think about that graph, 1, 2, 3 units, hopefully you remember a little bit that graph looks something like that. Now, the fact is that some people would say, well, x is equal to 3, that's a critical point. We technically don't say it's a critical point because it's not actually part of the domain to begin with. So you can see, yeah, you can't take the derivative at 3, but 3 isn't part of the domain anyway. So it's a little subtlety in the definition of what we call a critical point. We say it has to exist in the domain first. So if it's undefined, we actually really don't say that it has a critical point at that spot. But for local max, local min, the corners, and vertical tangents, we consider those critical points. So find the critical numbers of the function. Confirm the critical numbers by sketching a graph of the function. So what do we need to do to find critical numbers? We take the derivative and we set it equal to 0. So 3x squared minus 4x plus 1 equals 0. This does factor to 3x minus 1 and x minus 1. So we have x values of 1/3 and 1. Are those actually part of the domain? Yes, they are. These are part of the domain because the domain for a polynomial is all real numbers. So we're good to go so far here. Okay, domain is all real numbers, so those are critical points. You could check the graphing calculator to confirm that those are in fact critical points. Okay, this example, we notice that x cannot be 0. So x can't be 0, so that's an example of a situation where you have an undefined value right away from the domain. So you want to find the derivative, f prime of x. I'm going to use a quotient rule. The derivative of the top is 2x times the bottom minus the bottom times, or the derivative of the bottom, which is 1, times x squared minus 1, all divided by x squared. And when you do that, you get 2x squared minus x squared plus 1 over x squared. Notice that gives me x squared plus 1 over x squared. Now, you could write it like that. You could also write it as if you were to divide each one of these by x squared. Notice you get 1 plus 1 over x squared. That would be the derivative as well. Either way, notice that you are looking where the derivative is equal to 0 or where it does not exist. So we set it equal to 0. The way that we're going to solve this, okay, I'll look back at the original one that I had, which was x squared plus 1 over x squared. So something is equal to 0 when the top is equal to 0. And the question is, can x squared plus 1 ever equal to 0? No, x squared plus 1 does not equal 0. Your solutions would be plus or minus I, right? X squared is equal to negative 1, and you square root both sides, plus or minus I. So no values where it's equal to 0 on the top. Now on the bottom, if you consider the bottom can't be 0, you might want to say, well, 0 is a critical point. But 0 is not part of the original domain. So we would say that this has no critical numbers. The next one, we have a absolute value function, and sometimes it's just good to just think about the absolute value function. If we would consider this as 3 times x minus 2, notice that this is just a absolute value function that's shifted to the right 2 units. And if you think about that, you don't really need to even consider the derivative. You know, in this situation, that the derivative does not exist at that spot. So x equals 2 is a critical point. Next one, a little bit trickier. You can take the cubed root of negatives, but the square root, you can't take square root of negative numbers. So therefore, my domain is from 0 to infinity. 0 to infinity is my domain. When I take the derivative, I'm first going to write the function as x to the 3 halves minus 2x to the 1 half. So the derivative is 3 over 2 x to the 1 half. Minus, if you drop the 1 half, we will have 1 over x to the 1 half. The 2's will cancel. 1 over x to the 1 half. And so I want to consider where this is equal to 0 or where the derivative does not exist. So 3x to the 1 half over 2 minus 1 over x to the 1 half equals 0. Let's solve that. I will first find common denominators. I multiply top and bottom by x to the 1 half. Multiply top and bottom by 2. And I get 3x minus 2 over 2x to the 1 half. So when is the top equal to 0? The top is equal to 0 at x equals 2/3. Is 2/3 part of the original domain? Yes, it is. The domain is from 0 to infinity. And then, where does the derivative not exist? Well, wherever the bottom is equal to 0, and that would be at 0. Is 0 part of the original domain? It is. And so 0 and 2/3 are, in fact, my critical points. If I can just show you, it's to confirm your answer by looking at the graph. If you look at this graph, I have the square root of x raised to the 3rd power, then minus 2 roots of x. And if I zoom 6 and I check out this graph, notice that the graph from 0 to infinity, that is the domain. I have that correct. I'm just going to change my window a little bit here. I'm going to make it so that my y minimum is -4 and my x minimum is just -2, so I can get a better look at this graph. Look at what happens there. As you trace this, notice that as you head on down, we said our critical values are at 2/3. Notice at 0.6 repeating. What happens is the derivative is equal to 0 down there. So we've confirmed that, and if you go over to 0, you would get the endpoint, the starting point of the function, and you can't take the derivative of the starting point. So it confirms for me that 0 and 2/3 are in fact the critical points. The algebra found it for us. The next one, the bottom is never equal to 0. So domain is all real numbers. Let's take the derivative, f prime of t. I use the quotient rule. Derivative of the top is 1 times t squared plus 1 minus the top times the derivative of the bottom, all divided by the bottom squared. So f prime of t is equal to t squared minus 2t squared is negative t squared. So 1 minus t squared over t squared plus 1 quantity squared. That should look familiar. It's something that you did on your last unit. Where is that equal to 0? The top is equal to 0 at 1 and negative 1. The bottom is never equal to 0. So I would say that we have, in fact, these critical values of 1 and negative 1. If I confirm that graphically, you can tell x divided by x squared plus 1. And if I zoom 6 and you check out the function, it doesn't really look like a whole lot to the function. If we just change our windows so that our y minimum is negative 1 and our y max is positive 1, now look at the graph. So it looks like we should have critical values wherever the derivative is 0, which is down here at an x value of negative 1, and up here at x value of positive 1, which is what we thought. Isn't that nice? Next one, cubed root of 3 minus x. Again, if you have an idea of what the function looks like ahead of time, hopefully you remember that your cubed root function looks like this. This one, though, is going to be shifted 3 units to the right, and it's going to be upside down, or I say a horizontal flip. And you can see that you do have a vertical tangent at x is equal to 3. I can tell right away I'm going to have a critical number of 3. Let's go through the calculus to see why. First of all, domain of a cubed root is all real numbers. And this is g of y, g of x, sorry about that. Let's take the derivative. I'm going to use the chain rule. U to the 1/3 and 3 minus x. The derivative of u to the 1/3 is 1 over 3 u to the 2/3. And the derivative of 3 minus x is negative 1. So therefore, g prime of x is negative 1 over 3 times 3 minus x to the 2/3 power. So if you consider where is negative 1 over 3 times 3 minus x raised to the 2/3 power, where is equal to 0? The top is never equal to 0. The bottom is equal to 0 at x equals 3. That's where the derivative would not exist. And so you can tell by the original graph that we produced that that is the case. Okay. All right, we're almost done here. Letter G, x to the 2/3 divided by 4. This is the famous bird function. Looks like that. So you can tell that you should have a critical value at just 0. Let's confirm that. Y prime is equal to, first of all, this is 1/4 x to the 2/3. So divided by 4 is the same as multiplying by 1/4. So we would get 1 over 6 x to the negative 1/3. So y prime is equal to 1 over 6 x to the 1/3. So where is that equal to 0? Well, the top is never equal to 0, but the bottom is x equals 0. And you can tell that, in fact, by the graph, that's where you have a critical value. Last one. Don't know what this graph looks like. We do know that the domain is all real numbers, cosine and cosine. Move on forever in the horizontal direction. Y prime. We're going to try the derivative without using the boxes, folks. Derivative of the inside is 2, so 2 times cosine of 2x. And then 2, derivative cosine is negative sine, so negative 2 sine of 2x. So we're wondering where this is equal to 0. So 2 cosine of 2x equals to sine of 2x. If I divide both sides by 2 cosine of 2x, notice what you get. We get 1 is equal to tangent of 2x. Where is tangent equal to 1? Where is tangent equal to 1? Well, if you consider on your unit circle, tangent is y divided by x. So where do you have y divided by x and they are the same? Well, there and there, the y and x would be the same. That would be pi over 4, and that would be 5 pi over 4. And it would just continue to every time you go halfway around a circle, so every pi units, it would be, you'd continue to have those values. So when we inverse that, where is tangent equal to 1? The pi over 4 is then equal to 2x. If we divide by 2, we get x is equal to pi over 8. And if you look at your, so that's just one of the values. We won't go on extensively to find all of them. There's an infinite number. But if we go into this function and we type in, what do we have here? We have 2, or sine of 2x, sine of 2x plus cosine of 2x. And you want to look at the function. It's kind of some interesting behaviors about it. There it is. We'll change it so that, my window, I'm going to go to y minimum of -3, y maximum of +3. Okay, make sure that you're in radians when you graph it. Looks very similar to a sine and cosine function. If you went ahead and tried to take pi divided by 8, notice it's 0.392. And on your graph, if you take the x value to 0.39, we'll go to trace, sorry. Notice when you get up to the 0.39 spot, there, sure enough, it is. You have your 0.42, but we're close to that 0.39. That's where the derivative is equal to 0. And if you continue along, you'd have another one down there. So we have an infinite number of them. We just found the first one. We're not going to make you find all of them. There's a way to write that response, but kind of taking that out of our time this year is just a little bit more than what we need. But again, you've confirmed that that is in fact a critical value. Don't worry about example 3. I think we're good to go. Thanks for paying attention, and we look forward to seeing you guys soon. Enjoy the beautiful weather.